Hello. In this video we're going to talk about copulas, and it's um, it's an introductory module on the motivation for usage of the copulas, and I'm going to I'm going to use copulas for estimating the joint distributions. In this video I'm going to talk about why would we be using copulas for that purpose. So first let's talk about where the joint distributions arise. And in financial industry or in economics, they're pretty much everywhere. One example I'll give you here is the joint distribution of daily returns of S&P 500 index and so-called VIX index. VIX index is sometimes called fear index, and it captures the volatility of options trading on S&P 500 index. Actually, the creator of the VIX index itself, economist, he calls it a fear index too. Without going into details of what it is, I'll say that S&P 500 index has a lot of options traded on it in the options market. So this VIX is an index which tracks the volatility of at the money or around at the money options on S&P. So before going any further, let's look at this plot which I drew myself, and I pulled the data. I don't remember exactly what was the data range, but the data was S&P index, S&P 500 SPX index, so-called, and VIX index. And then what I did was I got the daily log returns. So I think it was about 1 year worth of data, if I'm not mistaken. Now, if you draw the scatter plot with S&P log returns on x-axis and VIX log returns on y-axis, you could see that there is a structure emerging here. So when S&P increases on a daily basis, VIX tends to decrease usually, right? So let's see what's going on here, right? So when S&P is going to the right, which means it's increasing, VIX tends to decrease, and when S&P drops, VIX tends to increase. And if you are listening me in 2020, I'm sure you have noticed it in March, right? In March 2020 we had the record VIX. It was the highest VIX. So VIX means VIX reflects what what traders think of the volatility of S&P index. So they must be somehow related, and we see that there's clearly a correlation structure there. But I'm not looking at the correlation in this plot. What I'm looking at is the probability distribution. So suppose the question you may ask yourself is, what is the probability that daily return on S&P will be, let's say, 5%. That is, by the way, should be very low probability, and you see there's only a few observations here. And then you might ask yourself, but what is the probability of VIX dropping maybe 20% on log return base? And again, you see some observations, not a lot, because that's pretty big drop. But the joint distribution answers the question as follows. What is the probability that S&P index maybe goes up by 3% and VIX goes up by 1%, right? So if you look at this scatter plot, then you could see, well, 3% is probably around here for S&P, but then we are asking what is the probability that S&P will go up by 3 and VIX will go up by let's say 1%. So that's why it's called joint distribution, right? We're looking at the joint probability, and I'm circling this area where I think uh, where I think the probability should reside, and we see there's no observations in this point. So if I'm building my probability distribution, joint probability distribution based on this data, it'll be very difficult for me to estimate what is the probability in this circle I'm circling, right? Why? Because there's no observations there. I would have to somehow imply what is going on in this corner, or let's say top right corner, based on the data truly in the middle or maybe on the diagonal. And there's no data in that rightmost corner, right top corner. And that should make estimation very, very difficult, right? So unless I know exact functional form of the distribution, and then I'll fit my distribution here and that form, it's impossible actually to estimate the probability here without a parametric estimation, and I'm not going to talk about it here. Right, so that is where that's one example where joint probability distribution can arise. Right now, I only looked at two series. Okay, this is bivariate distribution, but actually, even just staying within the options example, which is close to what I do at work, I'll say the following. Well, actually, what VIX does, it tracks 30-day at the money volatilities, right? So when you have options, it's derivatives products on equities. They have different strike prices. So, for instance, a call option at 1500 SPX in 30 days would mean that in 30 days you can buy S&P index by you can't buy an index, but for a second just think you can buy an index for 1500. So currently S&P, as you know, is in 2000s, right? So if the S&P were to drop a lot, then maybe this option would be in the money, but that's not what's important here. Sorry, for a call option, actually, it is in the money right now, right? If it's 1500, so it must be very expensive call option. But the point here I'm saying is that there are different strike prices. I mentioned 1500, but there's a whole array of strike prices, and if you look at the volatilities of these strike prices, they often form what is called a skew or a smile. It sort of looks like a smile, I guess, to some people. That's why they're called like that. But the point I'm bringing here is that every point on this smile or a skew can be interesting to us, and we might not can be if you are in let's say in risk management on equities, every point is interesting to you. It's interesting to me. So in that regard, you might be interested in building joint probability distribution of each of this point and maybe also S&P index, right? So that way you see there's a lot of points here, at least let's say 40. So you have a 40-dimensional joint distribution, not just S&P and VIX, but S&P and volatility, let's say 1500, 15 and 50, 16, and so on and so on. So that way, it's a bit difficult to imagine, but it's a hypercube, so it's not two-dimensional square anymore. It can be a cube, right? If you're just using two strikes in one underlying index. But if you're going after 40, it's 40-dimensional hypercube. I cannot I can't even envision like a 4-dimensional cube. That's difficult. I cannot do it at all. But 3-dimensional I can. And now imagine it could be 20, 30, 40, or 1000, whatever. So that's how these joint probabilities come to the picture in, let's say, in finance or economics. That's because we have time series of interesting variables to us, right? And we might be interested in joint distributions of maybe changes in these time series and so on. So, okay, good. We figured there are joint distributions, and we might be interested in building sometimes or often the joint probability distributions of these many variables, right? So, so I will not. I decided that for this motivation video, I'm going to use I'm going to use what I call a toy example here, not the real ones which we will use for our exercises and assignments, right, in the class. I called it toy, but it really is not a toy example to people who wrote this paper. It's from this website which I'm giving you the URL for, so you can pull the data and build it yourself. But there's this data set in which there are a few variables, and if okay, let's just take a look at how many variables are there. Oh, you see there's a lot of variables there. There's at least 24 or so variables, right? So right there you have this joint distribution potentially with 20 variables and so on. I pulled two of them so that we confine ourselves into two-dimensional space, which is easy for us to manipulate in our minds, and it's easier to understand certain things on two-dimensional case. And two dimensions are weight and height. So these are some biometric characteristics of people, and there's 507 people, persons, men and women, some adults, and so on. And what I did here is I just drew the scatter plot. Height is on horizontal axis and weight on vertical. So again, interestingly, taller people tend to be somewhat heavier, right? You see. So, and maybe shorter people are lighter, and so on. So there's some sort of an interesting pattern here. But what we again might be interested in, maybe building the probability, joint probability distribution. What's the probability that a person will have a weight, let's say between 40 and 50 kilograms, and height 180 centimeters and 190? It would be in this cell, right? Not a, well, there's no observations, hard to say. Yeah, 6 foot tall person with 40 kilograms, that's probably not easy to find, right? So how could we build the joint distribution? So I'll show you first a couple of charts, and then we'll go and actually look at Excel code which does it. So we could start with the following. So let's build a grid. So maybe we'll divide this the space into maybe two parts, left, right, and top and bottom, and that's what I did here, right? So I have exactly two. I have 4 cells basically, and how am I doing it? I'm taking this whole range from 140 to 200, and I'm just dividing it by 2. So I have 180 to 170 and 170 to 200. I'm doing the same. I'm having two. I'm having, how would I say? I'm having 2 grid points, right, in vertical axis too, which is a weight. So my weight is going to be from 40 to 80, 80 to 120. So my weight step is about 40 kilograms. And when I do that, I have 4 cells, right? Two horizontal, 2 vertical, which is 2 by height and 2 by weight. And I'll end up with 4 cells, and then I can just count the number of observations which fall into these 4 cells. And when I do that, what do I get? I get this nice, rather simple, I would say, histogram, right? In this case, I called PDF. I already converted into a probability density function. So we have a very simple density function with 4 points on it, but there's not a lot of detail there. So we might be interested in maybe learning a little more, maybe looking at a more granular picture of this PDF, because if I'm interested in, say, 180 to 190 height, well, then I can't. It's a bit different here, right? They're all going into one cell, so I want to have more granularity. So let's try that.